Okay, but now the important thing is to identify that, oh, that's exactly the binomial random variable. Okay, and that shows you how commonly this type of experiment is occurring, and you're interested in the number of successes. Okay, and that just shows you, that we now have the tools to compute the probability of the number of successes. Okay, so now let's discuss the exponential random variable, or what's called the waiting time. Okay, so the waiting time. Okay, so it's a very similar experiment. It's basically the same experiment. Okay, the only difference. So you have a success probability. So you're trying something, and each time you try, you may either succeed or fail, and each trial is independent. So the conditions of this experiment are: you repeatedly try. So independent trials. Okay, and independent trials, and each trial has the same probability of success. Okay, so each trial has the same probability of success. Okay, so you try, you fail, you try, you fail, you try, you fail. We do this all the time on the internet. We try to send a packet, and if it succeeds, we're done. Okay, if it fails, we try again. If it succeeds, we're done. If it fails, we try again. Now the chances of success when we try to send a packet are very, very high, 99.99%. Okay, maybe, but there's still a small chance of failure. Okay, so each trial has the same probability of success. Let's call it P. Okay, now what's the difference? Unlike the binomial random variable where you have a fixed number of trials, in the waiting time, there's no fixed number of trials. You just keep trying until you succeed. You just try, fail, try, fail, try, fail, try, succeed, done. Okay. So a lot of couples play this game with girls. They keep trying until they have a girl. So that was Malik's game. We kept boy, okay, boy, okay, boy. Then finally girls stop. Okay. So, so this process, this experiment where you keep trying something until you succeed is very popular. Just like you keep trying something a fixed number of trials. Okay, it's a very common experiment that we'll do in practice. Okay, in many scenarios. So let's analyze it. Okay, now what are we interested in? What's the measurement we're going to make for this experiment? The measurement we're going to make is how many trials did you make? Okay, so the random variable we're interested in is the number of trials to success. Or maybe I should say till success. Okay. So how many trials did you make until you succeeded? Okay. Now here, it's very convenient to just draw the outcome tree. Okay. So, you start your experiment. Okay. And we played this. We did exactly this in the very first lecture when we said you keep tossing a coin until you get a heads. How many coin flips did you make? That's exactly the waiting time. The waiting time to the first head. Okay. Sometimes we might say, I'm waiting till the second head. So you're having kids until you have your second girl. So then what's the waiting time till 2 girls? Okay. But here, we're considering the most basic version of this experiment. You're waiting till the first success. Okay. And so I'll do it quickly. You can either succeed on the first trial. So I'll do that as a success. Okay. So that's a success with probability P, or with probability 1 minus P, you fail. Okay, but then in the second trial, you might succeed with probability P, or you fail. Okay, or then in the third trial, 1, 2, 3, you might succeed, probability P, or you fail. Succeed or fail. Succeed or fail. And this could, in principle, go on forever. I mean, in practice, it'll always end. Okay, but in principle, it could go on for a very long time, even. Okay, so each failure is 1 minus P, 1 minus P, 1 minus P, 1 minus P. Okay. And so this outcome has probability P. This outcome has probability 1 minus P times P. This outcome here has 1 minus P squared times P. This outcome 1 minus P cubed times P. 1 minus P to the 4th times P. And you get the pattern. Okay. Now, let's see this random variable we're interested in, which is the number of trials till success. What is x? Well, here it's 1, here it's 2 trials, here it's 3, here it's 4, here it's 5, and so on. And it's not going to take, too much trouble to notice the pattern. Okay, well, the number of the probability to take k trials means you fail k minus 1 times, and then you succeed. Well, since each trial is independent, the probability of k minus 1 failures is 1 minus p raised to the power k minus 1, and then you succeed p, and that gives you k trials. Okay? So the probability of k trials to first success is exactly equal to p times 1 minus p to the k minus 1. And we very often like to write this as p over 1 minus p times 1 minus p to the k. So I just, I divided by 1 minus p and multiplied by 1 minus p. And we often write this as beta times 1 minus p to the k, where beta is this guy, p over 1 minus p. Okay? And one of the advantages of writing it this way is that it becomes immediately obvious why we call this the exponential random variable. Because look, the probability that you have to wait k trials to the first success is exponentially decreasing in k. The probability of k trials is some constant, well, the constant happens to be p over 1 minus p, times 1 minus p to the k, exponential in k. Okay? And so this is why it's called the exponential random variable. Exponential in k. Okay. And that's it. That's the exponential random variable. Okay. So now we could compare the binomial and the exponential random variable. And I ask you to go and plot this. So pick a value of n. Okay. Well, let's say n equals 20. And so, for example, p equals 1. Let's say p equals 1/4 or something. If you plot the PDF, if you plot this PDF, you'll see, just like what we saw here, there's a peak. Okay, so when n equals 15 and p equals 1/5, so n equals 15 and p equals 1/5, we see that the peak is at 3. So the possible values are 0, 1, 2, 3, up to 15. Okay, and the distribution is rising up to 3, so it's going up. And then it starts coming down. Okay, and basically hits 0. Okay, and if you take n large and p a constant, or p, let's say p not going to either 1 or 0, so as n becomes larger and larger, this approaches the very familiar, what you might be very familiar as the bell-shaped curve, or the bell curve. Okay, which basically mathematically is what we call the Gaussian distribution. So this is approaches a typical bell-shaped distribution. If you look at this probability distribution function, so if I plotted it, okay, so the most likely choice, the most likely number of trials, okay, so beta is a constant. So this guy is decreasing with k. The chances that you have to make more and more trials is decreasing with k. So it's it starts off somewhere, and then it starts dropping, and it drops very quickly to 0. Okay, and that's the exponential distribution. Okay, so let's do an example of the exponential distribution. Example. Very cute example. And this is going to show you again that, when we try to solve problems algorithmically, sometimes we cannot avoid using randomness. So this is now to seal the deal that certain things that we like to do, you cannot do them without randomness. And this experiment is going to come into play. This waiting time, this exponential distribution. So what's that experiment? There's a router. So there's a router. And you and let's say 3 other people, so Alice and Barb, are trying to access this router. Bam. So imagine time steps 1, 2, 3, 4, 5, and so on. If exactly one person tries to access the router gives you access, and you can communicate with the rest of the world. If more than one person tries to access the router at any given time, the router gets confused and it just says it blocks the access because it cannot service two requests at the same time. Okay, so simple strategy for you, Alice, and Barb. At every time step, you all try to access the router deterministically. So deterministically, everyone tries to access, okay, at every time step. Okay. And it's not just routers that face this issue, databases, database servers, when multiple people try to access. So the greedy thing to do is at every time step, who else is there in the world? Nobody else, just me. Let me try to access. So everybody tries to access. Fail. Okay. So what will happen here? What's called deadlock. Nobody will ever gain access to the router. Okay. So the only solution is what's called random backoff. Okay. Now, the actual routing protocols that are in your Wi-Fi card and in the router do what's called random, not only random backoff, but random exponential backoff. So they do more sophisticated things. But the simplest thing you could do is say, you know what? It doesn't make sense for me to access at every time step because then, if someone else is doing the same thing, we're just going to clash all the time. So instead, let me randomly access. Let me decide randomly whether to access, let's say with probability 1/3. So everyone accesses with probability 1/3, okay, at each step. Okay. So now it is possible that all three people access at the same time and then it's a failure. Okay. But let's see, what are your chances of success on any given step? So you access with probability 1/3 and you need the other two people not to access with probability 2/3. So they're not going to be accessing with probability 2/3. So probability of you and not A and not B by independence, so we assume that each of you independently tosses a coin or a random number generator in order to decide whether to access, and you access with probability 1/3. So probability of you and not A and not B is equal to 1/3 times 2/3 times 2/3 equals 4/27. So that's your chances of success on a given trial. And you're going to keep trying to access this router, keep trying until you succeed. It's exactly this experiment. So let's see, what are your chances that you access on the first shot is 4/27. Okay. What are your chances that you have to wait for the second trial? Okay, it's exactly this experiment. And we can compute it. Okay, so we can compute beta is 4/27 divided by 1 minus 4/27. Okay, and so then we can compute, the probability. So K is 1, 2, 3, 4, 5, 6, 7, and so on. And what's your probability that you have to wait for one trial? So the probability that you have to wait for one trial is about 15%. There's about 15% chance that you will succeed on the first trial. Okay. The second trial, about 13%. The third trial, about 11%. The fourth trial, about 10%. Well, more like 9%. The fifth trial, about 8%. Okay, and the sixth trial, about 7%. The seventh trial, about 6%. The eighth trial, and so on. Okay. Approximately 50% chance that you won't have to wait more than 4 trials. Okay, which is reasonable. Okay, so which is not only reasonable, but it is way better than deterministic access by everyone, which is just complete deadlock. Okay. So this is an example where if we don't put randomness into the algorithm, there's no way for us to in any principled way avoid this deadlock. Okay. So you might say, everybody, instead of accessing at every time step, access every third time step. Okay. So Malik, your accessing time steps are 1, 4, 7, and so on. Alice, you are 2, 5, 8, and so on. Okay. Now you think that everyone gets 100% success, right? Okay. and they will be accessing 1 in every 3. So this is not much worse. You have to wait just for 4 trials, let's say typically. Okay? And if everyone were totally synchronized, we could get everyone accessing 1 in 3 trials. So this is pretty good. Okay, but now can someone tell me what is the problem with the, every 3rd trial for Malik, and then offset by 1, every 3rd trial for Alice, offset by 1, every 3rd trial for Barb? Can someone tell me the problem? Okay, well, there are lots of problems. The first is, what if someone else comes in now? Okay, but let's assume someone else doesn't come in. The bigger problem is, well, what if we don't know when Alice is going to arrive to play this game? So what if Alice arrives to play this game on time step 3? So you told Alice you can't access on time step 3. You must wait, because that for Alice is time step 1. You must wait till time step 2, which is 4, which is exactly when Malik accesses. Okay, so having deterministic offsets is not going to work, because, that requires people to be in some sense synchronized. They all agree on what time step 1 is. Okay, not easy to accomplish such synchronization in a distributed way. You have to take the distributed algorithms course if you want to learn how to do those kinds of things. Okay, so, and even if you manage perfect synchronization, you only get to access every 3rd try. And this random approach, which doesn't require any synchronization, gets access of approximately every 4th or 5th try. So it's not much worse. So you don't even need to invest in synchronization. Randomness saves the day. That's probability at work when it comes to designing algorithms. Okay, so what did we discuss today? Today, we talked about the very practical, issue of, you have complex experiments in practice, but we're not interested in complex outcomes. So we summarize the complex experiment into a random variable. Okay. The random variable summarizes the complex experiment into a measurement, and then what we're really, all we care about is what are the possible values for that measurement and their probabilities. And then once we have the PDF for the random variable, we don't really need to work with the complex outcome space for the experiment. We just work with the random variable. And then we talked about a lot of the random variables that are going to arise in practice: the Bernoulli, the uniform, the binomial, big ticket, and the waiting time, big ticket. Okay. So now, we're sort of positioned to go and analyze even more complex experiments. Okay. See you next time.